The following is brought to you by Total Seal Piston Rings, the leader in ring seal technology. TotalSeal.com. Hey everybody, welcome back to another episode of Hidden Horsepower presented by Total Seal Piston Rings. My name's Joe Castello, and we have got another great episode for you. Joining me as co-host on this episode, he's back, Lake Speed Jr. Lake, welcome back. How are you?
Thank you, Joe. Yeah, it's been a while, but I've been listening intently. You and Keith have had some great guests on recently. It's fun to be a listener of the podcast, not just a participant, but, I will gladly take my turn at the co-host chair today and see if we can't do a good job.
Well, I think it's actually breaking down in a very interesting way. Like Keith kind of comes on with the drivers and drag racing and engine builders. You kind of come on with the scientists and the metrologists and people in the NASCAR universe, right? There's like everybody's got their domain over there at Total Seal.
That's a great way of saying it, right? The episode we did with Dr. Neil Cantor earlier in the year actually is very popular. In fact, within the STLE crowd, I was at the STLE, and STLE, just for people that want to know, is a Society of Tribologists and Lubrication Engineers. It's the Oil Nerd annual convention. It was last week, and I got to go there, and it was fun, and people mentioned the podcast. So there you go, Hidden Horsepower, reaching a whole new demographic.
Wow, that's great. And that's what this podcast is about. It's about attacking the right person with the right subject at the right time. But really, everybody wants to know, how did the Lake Speed autograph session go at the Tribologist Convention?
Well, the great thing is I actually ran into our guest today at the event, and I didn't even know he was there. But it was like we were sitting in the same session because we had the same interest. So I was like, hey, we should bring you on Hidden Horsepower again for your own episode, because he was with us for one of the PRI episodes with Brad Lagman. So that's why I say, Mark, can you be on? And so here we are today to bring Mark Malburg onto Hidden Horsepower to really dig deep into surface finish, texture, shape. I mean, Mark's a brilliant, brilliant guy his work is phenomenal. I actually was looking at some projects today, and I'm looking at parameters that he created. So when we're talking surface finish, there's no one better to be speaking with than Mark Malburg.
So let's bring him on. Instead of just talking about him in front of him, which I'm sure he loves, from Digital Metrology, Mr. Mark Malburg, again on Hidden Horsepower, but this time his own feature. Mark, welcome. How are you?
Fantastic. It's great to be here. It's pretty hard to sit here and listen to you guys talk like that. I'm just a regular guy that even dressed like Lake during STLE. There's a pic online. It's like we got the same memo.
The Tribologist's uniform.
That's right. Exactly.
No, I think it's great, and I was following you guys on social, of course. That tells you a lot about me. But I thought it was funny that you guys buddied up. But the point is, this is knowledge that people need. People that are in these fields, people that are interested, you're pushing the envelope with what the understanding is about surface finish. And you guys are I don't know if you're blazing a trail or you're following a trail, but the bottom line is you're interested and you're going after it.
Yeah, and I think it's really ripe timing. I know Lake is out in the forefront, really opening eyes for a lot of people. I've come at this from a more industrial base where big companies have kind of already been there. They've had to be pushed because of things like emissions, where now all of that learning is helping us push performance in the racing world.
Isn't that interesting, Joe? For years it was always the racing guys that would, R&D out these new parts and kind of do the proof of concept. And the OEMs would kind of notice, oh, this is going on over here in racing. Now it'll trickle its way into production cars. But in this case, it's actually the reverse. We have engineering that's been fundamental in production vehicles for a while now, making its way into racing. I think it's kind of cool to see the two-way street now forming between industry in motorsports and how it can be beneficial for both sides.
It's a leapfrog kind of thing, isn't it? One leads for a while and the other leads for a while. And it's great that we now have these lines of communication between the two, even through things like STLE.
What's interesting is
Right.
Billy Godbold was the first one to ever say that on Hidden Horsepower, Lake, that it was actually emissions standards that forced these OE manufacturers to start looking into all of this. Otherwise, if that standard hadn't been put out there, like some crazy number that they had to hit, they would not have received the motivation to go into all of these areas that now we're reaping the benefits. I think that's also just shocking and mind-blowing and certainly contrary to, normal logic.
Oh, it is. And I don't think we're done. When we were at the STLE conference last week, there were a couple of gentlemen from Nissan were there giving the keynote speech, and they were talking about, well, what does the future look like? And looking all the way out to, say, 2050. Well, there's an electric car in their future. I'm actually they make the Nissan Leaf now. But what they said was, well, we can't tell you for certain that's a battery electric vehicle in the future. It might be a hydrogen fuel cell. But we also know that we're going to be building higher efficiency internal combustion engines for probably another 20 or 30 years. We want to take regular internal combustion and do things like, in their case, variable compression. And they were speaking about how they had introduced, plasma spray bore, which we'll talk a little bit about, the spray bore coatings and things and how that relates to surface finish during this episode. So I don't want to give it all away right now, but they also mentioned, they're running DLC coated lifters, and they were texturing those lifters in order to have better efficiency, especially longer life, lower friction. Well, DLC coatings have been used in NASCAR for at least 20 years at this point. So this is one of those cases where you had that symbiosis, that two-way street between industry and racing, where racing pioneered something that's made its way into production vehicles, but now that some of that production technology is going to head back into racing vehicles, because their whole point is we need to have higher efficiency engines, whether that engine is actually driving the car or whether that engine is actually creating electricity for an electric car, where they call it a series parallel, where there's still an internal combustion engine, but it's there just to generate electricity. And they see that as a step, of course, as a standalone engine, to be actually a generator, if you will. It can be very, very efficient. So that's the whole goal. So that's what I'm thinking, is that it's been great to see this evolution the last 10 years of that symbiosis between industry and motorsports. I think we're going to see that grow in the next 10 years. And conferences like STLE, and what we're doing a webinar with them in about 2 weeks, actually, about this topic of how can racing help support industry in the growth in tribology. How can we make engines more efficient? I think we can make them a lot more efficient. And I'm excited about Mark's, his take, because that's really the key to unlocking that hidden horsepower. I know, pun, bad pun. I get it. But that hidden horsepower can really be unlocked through surface finish technology, not just having whatever surface your machining process left you, but creating a surface finish that's engineered, that provides better performance, better durability. That's what we're talking about today.
I think that's absolutely the case, and it's interesting because the two industries have come at things almost two different ways. If you think about racing, it's about containing combustion, getting the most out of the fuel. In the production world of on the road vehicles, we've almost come the other way of really trying to control the oil to not let it get up and combust and make dirty exhaust. So in either case, we're working with that seal, that piston ring, and both of us were trying to optimize it. Now I say both of us because most of my customer base has been high volume production engines, and I only get to dabble in the fun stuff of racing. But in either case, and it's this this combustion containment that we're all fighting or trying to optimize. And it really does come down to looking beyond the obvious. I mean, the obvious is make a bore with a certain roughness. Well, anybody can make a bore of a certain RA roughness, a certain average roughness. But where we can differentiate ourselves, whether it's in production or in racing, is by optimizing that texture. And that's where I think we're all trying to get there, and we may actually all end up in the same place because it is optimizing a sealing surface against a piston ring.
Well, and that idea of that optimal surface, right, for seal, it really goes back to the fact that oil is the gasket between the piston ring and the cylinder wall. And it's no different than what Nissan was talking about with their textured DLC-coated cam follower, is that they need to have oil in between that cam lobe and that cam follower in order to lubricate that cam follower. But they've created this texture. So DLC is diamond-like carbon, and it is a very hard, very low friction coating that adheres to that surface of that lifter. Again, we've used them in NASCAR for a very long time. It's fantastic durability, very low friction, but you still have to retain oil on that surface. We learned the hard way in NASCAR. We didn't have contact like Mark back when I was at Gibbs, and we just know that as we started polishing the camshafts and making them smoother, things got better. So if a little is good, well, more must be better, right? So we just polished them mirror smooth and got the RA, the roughness average, less than 2. Well, then we started burning cams up because we didn't have enough oil retention. So we had this surface so smooth that there was basically began to have what's called adhesion. There's no lubricant trapped there to keep the two parts from wanting to stick to each other. Well, the flip side of that spectrum is adhesion, where it's so rough it becomes like coarse sandpaper and it's just ripping at the surface. So back to Nissan, what have they done? They've created a very low friction engineered surface with the correct texture to retain the oil to lubricate that component. On the piston ring side, what Mark was talking about is we need this engineered surface that can hold the oil to both lubricate the piston ring and the cylinder wall, but also function as the seal. Because if there's no oil on the cylinder wall, that when that piston ring is moving so quickly as it's skiing down it, it has to have that oil film in order to provide the gasket, if you will. Just like there's an engine, you've got a cylinder head and you've got a block. Well, it's the head gasket that helps to seal between the two. Think of oil as the gasket. Think of these surface textures as the reservoirs that can hold that oil to make it available to do that job. And that's what Mark's talking about, which is why, and I'll let Mark explain why the RA, the roughness average, isn't a really good guide to what your surface is. It can tell you one thing about the surface, but it's not going to be able to tell you all the things you need to know about that surface.
Right, like it's a case where if we're really going to optimize a surface, we're not just going to choose making it rough or smooth. It's making it the right kind of rough. For example, we wouldn't want a surface that looks like a spiky dog collar. So a surface that has downward valleys, not upward spikes, is very important. So if we can start to think of a cylinder bore surface really as an upper surface that we're going to slide on and a lower surface for carrying lubrication and collecting garbage, we can start optimizing both sides. Come up with peaks that are nice for sliding, come up with valleys that are nice for oil and garbage collection. And then we start walking that line of how much of each do you need for each application. And each engine, even within, a range of products, a range of horsepowers, that balance may be different. I like to think of it as tuning what are the two honing processes, peaks and valleys, and what are the two things the engine needs, peaks and valleys, and matching those things up. So matching a process to a shape that's going to give you the performance you want out of that particular engine. Now, we have kind of a theory in the production side of engines where we want that oil film to seal the piston ring all the way up to top dead center, and then the last micro drop of oil is gone at top dead center, and the only thing that combusts is fuel. There's no longer any oil in the interface at that last moment, and that last little bit of oil is blown down by combustion gases, which do not go past the ring. So it's this interesting balance of keeping things lubricated until right at the point of combustion. Because if you do have oil sitting between the ring and the bore at combustion, it's going to burn. So there's this magic act of designing that surface. And an interesting fact, I work in all of surface finishes. I mean, I work on you name it, whether it's consumer products, electronics, engines. And of all of the surfaces that are studied and researched around the world, there are more papers published on cylinder bores than anything else. The most engineered surface in the world is a cylinder bore.
Wow. So it's got to freak you out when you see somebody with like a 220 grit dingle ball hone just going to town in the back of the truck.
You're making me cringe, my friend.
Well,
where's the control?
Right. So it's interesting is last month, Joe, I got to go over to the UK and we did a little trip around and visited some of our customers over there, and we happened to stop at the National Rail Museum. And you're like, what does this have to do with anything? Just bear with me for a second. So the National Rail Museum there in York, England, has all of these old steam engines. So what people may not know is the piston ring was actually invented in 1852 for a steam locomotive. Way before there was ever even an internal combustion engine, there were piston rings. And where I'm going with this is, for years, cast iron rings were what people had, and this was commonplace. Well, then someone came up with the great idea of putting hard chrome on the face of the ring. It was still an iron ring to begin with, but you had a chrome face. But that was the interface between the ring and the cylinder wall, was this hard chrome. And that's where some of these ideas of hone it rough came from, because someone listening may be like, okay, I hear what you guys are saying, but we've always done this and we had good luck with it or good experience. Okay, we need to understand that the ring metrology, what material it is, what coatings are on that ring, have everything to do with the oil you use and the surface finish of the hone. It's a package. Joe's heard me say this before. It's ring seal soup. It's not a steak. It's a combination of all those things. So you have to look at these packages, and I think that's where sometimes this can be confusing or overwhelming to people. Like you said, Mark, it's the most studied, most published thing is cylinder bore finish. Well, why? Well, one of the reasons why is we have this variable that's been occurring over time, which is the advent of steel rings and different ring coatings. So you go from this old just cast iron ring to a cast iron ring with a chrome face coating. Well, that chrome face coating needed a different surface finish than regular cast iron. Well, then you go, to moly face rings where you're spraying in this moly coating because that's not as hard as chrome, so it's not as sensitive to break in. Because as anybody knows, old chrome rings, man, you have to do everything right and make sure you didn't even think about the word synthetic oil for your rings to break in. So if you even thought about synthetic oil with a chrome ring, it wouldn't break in. It was, just couldn't do it. Well, then the moly rings came along and things got better. But then as cylinder pressures began to rise and we got, more horsepower per cubic inch, well, then the moly began to find its limits. Well, then we came up with steel rings. And then within steel rings, you've got different PVD coatings. Back to how do you have that durability of that ring, that last micro inch of ring travel where it doesn't combust? Well, you have to have the correct coating on the ring to provide that lubricity, because you can't hold the oil because then it would burn. So it's the evolution of the ring materials and coatings that have necessitated an evolution in cylinder bore finish. And then we throw the other variable in there, which is the oil itself. You go from old school mineral-based oils to synthetic oils. You go from straight grade oils to now 020s and 520s, even 016 from the factories. All of these things have to be factored in. So as we were in one of the meetings last week, Mark, and the guy's like, why can't we just put one number on this? It's like, you can't. There's too many variables, right? You can't put one number on the surface. You can't put one number on the rings or the oil interface because it's dynamic, which makes it fun, by the way. I love it because there's so much opportunity here, Joe. If you think about, say pro stock racing and what those guys are trying to do, how tight that class is, where if you literally found a tenth of a second, you dominate the class. If you found 400ths of a second, you're really, really dominant in that class. So any kind of advantage you can find by adjusting that soup, that's important. That's big. So I think that's why this topic is so fascinating to so many people. And we hear people ask about this when we see them in the field, that, the podcast, we love talking about honing. It's like, all right, we got to get Mark on here and really begin to talk about these numbers. So Mark, why don't you tell them, okay, at RA, like you mentioned, isn't the right number. What are the right numbers, and how should we think about surface finish?
Yeah, it's a great question because, so I mentioned I work with people all over the world, and everywhere I go, not just engines, people think of roughness as a number. How rough is it? And roughness isn't a number any more than decibels tells me what band was playing. Roughness RA is just a number that says on the average how much are we wiggling up and down. And just like decibels is the amount of sound pressure, it could be a fire truck, a chainsaw, or a symphony. So to truly describe a surface, we're going to need more than just a single number. I tell people the first place to go beyond RA is the graph. And I know, like, you post pics of profilometers and graphs all the time, and it just makes me happy inside. It warms my heart to see that it's the picture that matters. And fun fact, the numbers vary. If I make a trace and then move over a couple thousandths of an inch and make another trace, it's an entirely different surface, especially with a crosshatched surface. You think of a trace where you cross two valleys, move over a little bit, and you might now trace through the intersection and only see one valley. So the numbers are going to move around, and people will say, I can't use a gauge that doesn't repeat. We have to remember the surface doesn't repeat depending on where you look at it. So first move beyond RA is the graph. I've found more and more people telling me they gain far more understanding by seeing how the picture varies, much more so than the numbers. Now, that's unpopular because I know we need numbers for contracts and we need numbers for process control, and we need the numbers. So the next move is to choose the numbers that reflect your shape.
Okay.
In the Digital Metrology Plateau Honing introduction that you mentioned. So in Surface Notes on digitalmetrology.com, there's a talk on Plateau Honing. There's one in Resources. You guys have seen the links and posted them as well, so thank you for that. But it talks about three different shapes of plateauing, or three different shapes really of honing. A surface that's kind of random, it's up and down. And then a surface that has a little bit more valley than it does peak. It kind of looks like some of the peaks might be knocked off, but it's hard to tell. And then there's the extreme surface. It looks like one guy described it as icicles hanging off your roof. Sorry for you people in the South. Sorry, Joe. Have you ever seen an icicle, Joe?
No, I haven't. That's the thing with it.
You've seen them on TV and movies, right?
I know what a popsicle is, though. Popsicles,
yeah, right,
I know.
popsicles.
Icicles, not so much.
Very different. Very, very different. Think of stalagmites, stalactites, whatever. So a surface that's crazy flat on top, broken up by valleys. Those three kinds of surfaces, the random one, the little bit too processed, plateau-ish, and then the super-duper plateau, are going to require three different ways of describing them with numbers. But basically, we're going to describe peaks and valleys separately. The RK family of parameters is super popular. It works for the middle class of surface, where we have RPK talking about the peaks that are going to get knocked off during break-in or worn away during break-in. RK is that running surface we're going to live on, and RVK describes the valleys. There's a lot more detail there, but that general trend of thinking of the pieces of the surface. When we get more extreme, there's a different set of parameters we can talk, in a different deep dive that are the Q family of parameters that are for extremely plateaued surfaces. But we need numbers to describe shapes, and there's never a single number like RA that gets us there. What I found was super interesting, Lake, on this topic of parameters was our conversation, I think, over a really sweaty, hot, humid lunch outdoors where we were talking about break-in and how, we can totally change the break-in dynamics with surface texture. And you'd experienced that recently yourself.
Oh, yes, it is. I mean, in fact, even a conversation I had today with a very successful team, very successful driver, mentioned that, oh, you know what, I had sat in on one of y'all's, trackside tech talks that we do, Joe, and he listened to what we were talking about. And he went back and he applied some of the lessons that we taught at that trackside tech talk. And sure enough, they have better consistency on braking. Whereas before, maybe 70% of the engines, ran perfect right out of the gate. And maybe 30% of them, there was something they had to chase or fight or maybe never quite got the way there. And they could never really put their finger on why it was. Well, once they changed the surface finish, all of a sudden that variability of performance disappeared, gone. Now they all break in the same. So yes, there's a huge impact on break-in just by affecting the surface finish values. The test we did a couple weeks ago at Ronnie Shaver's on our little mule engine that we've beaten to death over all these years, we had Brad Lagman change the hone. And as you said, we had more of that extreme plateaued. Now, we didn't go all the way where you've done some work, but we got it closer to that, where we had an RPK in that, we'll call it 8 to 12 range. So we've got median number of 10. And then we had the RK closer to 25 to 30. And then the RVK was in the 50 to 55 range. And that engine, I mean, it was sealed up from the time we turned it over. There was no breathing, nothing of that engine. And the blow-by was half of what it was previously. But previously it was really good compared to what we had seen before or to average. So it was incredibly low, and everything had to do with that. All we changed from the previous test was just the surface finish. Nothing else changed, and we were able to cut blow-by 50%. So that was pretty crazy just to see that big of a change off just changing those three numbers. But really what you're saying is it's more than those three numbers. If you looked at the previous graph, how inconsistent it was, that there was these ups and downs, it was that varied surface versus this past surface, which was much more consistently plateaued with some deep valleys along the way. That's what made the big difference.
Absolutely, and we see this in production engines, totally reducing break-in time. But even more important in high volume is knowing that consistency. We're not relying on let's roll the dice for 120 hours and see what the engine looks like then. We know right out of the box.
Right. Well, and that's the thing is that I can see it from an OEM level how important it is, because let's say you build 100,000 engines and you send them out the door. Well, that's 100,000 different customers. It's 100,000 different break-in procedures that will happen.
Exactly. Right.
And basically for whatever the different environments are, different thought processes. What does keep it under the red line mean to you? Well, some people mean that keep it at idle, and that's not good. Some guys are, well, it means it's 50 RPM under the red line. I'm good. There's all these variables. So as the OEM, well, what's the outcome of that engine? How many of those make it 100,000 miles before having a problem or have a blow-by issue? Well, if they can do things within their control of how they machine, what they use for rings and coatings and oil and surface finish, if they can change that soup to reduce the impact of those 100,000 different customers and how they choose to go about doing break-in, that's a huge gain for them. Because if they just do it we call it the old way of a single finish and then put it out there and hope the customers use the right oil, do the right procedure and all that, that's a big wish right there. They'll probably see some of those come back to them.
A good friend of mine said growing up he was taught that if you want to break in an engine and you want the engine to be fast, drive it fast during break-in. Where's the process control there? If you want it to be slow, drive it slow. There's some urban myths there.
And there are, right? And it goes back to some of them were founded within reason based on maybe during a certain period of time where there were certain coatings and surface finishes and lubricants of the day that was the right thing to do with what we knew at the time and the materials at the time. The problem is, like you said, these urban myths and legends persist, and then they get applied to a modern engine with different surfaces, different oils, different coatings, and that doesn't always work out. So the challenge is trying to come up with that surface that has very little break-in, where what the customer does to it has very little influence on how it's ultimately going to function. Because obviously we know that if we reduce blow-by, there's all kinds of great things that come from that. One, the engine's more efficient. So from a horsepower perspective, you got to love that. From an emission standpoint, that means, okay, there's less oil getting in there. All those things get eliminated, which is a good thing. But also you get less contamination of your oil, which means your oil is going to work better and live longer. So reducing blow-by is just a good thing all around, period. So how do you do it? And, talk a little bit about, Mark, what you've seen in terms of the evolution of the honing techniques, because I think it's one thing that I've noticed in doing these talks that gets people attention is the scale that's involved here. That we're not talking about hundreds of inches or even thousands of inches. So please go ahead.
Oh, yeah, and I think the processes have evolved trying to keep up with things like performance. So honing over time was a single pass, at least a single stone to make things round, cylindrical, and smooth-ish for the piston ring to do the heavy lifting of, final machining. And, the 1980s, this concept of plateau honing came into existence, or at least it became kind of a process, a name for something new where we honed it rough and smooth a little bit. But over time, we've refined that. We see, incredible variations that different systems, different engines require. I was looking at an engine that's part of a generator set, gen set, and a very, very different plateau. It was wide open, all kinds of big valleys, but a super smooth plateau. And so these textures have evolved based on applications. This particular engine that I was looking at, I thought it was a mistake. It had no material ratio. If you looked at it, it was all valleys, but the peaks were flat. It's just that it was a ton of valleys. And they were saying that's exactly the texture that's optimal for the durability that engine needed. Well, on the other hand, we can go all the way to the extreme of like an F1 sleeve, or even we touched on plasma, where we're going for very, very, very smooth textures with just an optimal, just enough in terms of valleys or porosity for lubrication and garbage collection. So it's hard to put my finger on an evolution because the path kind of splits. Once we learned that texture matters, different industries went in different directions to optimize their particular ring-to-bore interface. Now, one thing I don't want to leave in the dust here, because I talked about a couple of weird, super smooth examples, is there is a point where we go too smooth. And the term I hear in the world of surfaces is, oh, I want to make that surface better. And better sounds like shinier to most people. And you mentioned it with the DLC and other things. Smoother isn't always better. We need some texture in places. One thing that happens in the bore to ring interface is if we go too smooth, the shape or the geometry or the roundness of the bore can be a big factor. If you have an out-of-round bore, and I'm not saying just oval, I'm talking about head bolts causing distortion, little ripples along the roundness. Out of roundness is a killer if your roughness is too smooth. A smooth surface will not seal in. There's not the ability to machine away the peaks with a ring. So a bit of peak roughness is kind of a Band-Aid for bad roundness.
Okay. That makes sense. You think about some of the aluminum blocks engines out there, especially when they're trying to make them very large cubic inches, so that everything gets really thin walls, but you still have high compression. So I need really large studs in there to hold all this together that localize distortion. Not that the cylinder is not round. It still looks round to the naked eye, but there's these localized distortions that if it's too smooth, as you're saying, the ring can't follow. There's nothing there for it to actually seal against. So you'll have higher blow-by, you'll have more oil consumption, things like that, because you need to create enough roughness, as you mentioned, to Band-Aid so it can find its own spot once that distortion's already in place.
Right. You have a little bit of fuzz all over the surface, and then you trim away the fuzz on top of the lumps. And then you have uniform contact all over. Yeah.
Joe, who would be loving this right now is Nick Ferry, right? You think back up at the Nick Ferry episode we did at PRI with you and Keith. I listened to that recently. That's where he was kind of going with the whole hot honing thing that he loves, is that you're trying to closer simulate in the hone what the engine's going to be in its actual operating environment. That's why, using a torque plate, all of these different things are designed to try to simulate what that bore will really see in terms of stresses and temperatures in the car while it's in the hone. That way you can get it closer so you don't have to Band-Aid it as much, I believe is probably the best way of looking at it. Would you agree, Mark?
Absolutely. And it's not just, simply slapping a torque plate on and torquing it down. It's even torquing in the same sequence as assembly and the same gasket under the torque plate as you're going to use in the application. There is a lot of magic. I've seen cases where a wrongly applied torque plate actually causes more distortion when you go into the engine assembly. So
I can totally believe
it's
that.
a super important thing, yet it's something that requires some real care as well.
Last week one of the guys from Gehring gave a talk I was able to watch, and it was really interesting to see that evolution that he talked about. That in the 1970s when you had say chrome rings and things like that, how I had this single finish grit was how it was, and the engines lived 50,000 miles before that had to be rebuilt. Well, then you leap forward to the 90s, and you've got, Molly rings, and the finishes begin to be plateaued, and the cylinder can go 100,000 miles. Well, now they have these, the spray bore type cylinders with that porosity, that more of that extreme plateau, and you have steel rings, and now these cylinders are going 200, 300,000 miles. How, as the evolution of honing and rings and all that have come together, the longevity of these parts are going even further, and now they are even looking on the OE level. Okay, well, how do we replicate that outer roundness that's created by the distortion of the cylinder heads and the bolts and how they torque them and that whole process? And they were showing some examples from the Incometers and the Pat gauge results of how much change and distortion there is. And the top of those cylinders, especially near where the studs are, how they weren't even remotely close to round. They would be, you think about this circle, and then essentially you would have like convex protrusions, into the cylinder because of that, which is like, it's mind blowing. How can that be?
Well, part of that, Lake, is the plot scaling. There's more to unpack there, because when we plot roundness, we could take let's take a cue ball from your pool table. It looks spherical, and it is. It will roll. But when we do a roundness measurement in the world of metrology, we magnify errors. So even though it's convex, it may not be convex enough, and we plot it as concave. So I live in the world of roundness. I do commercial roundness systems, and it blows my mind when I see a plot. And it's even hard for me after 30 years of this to unpack a roundness graph. Is that cylinder bore really concave and convex? No, it's still circular, but our plot distorts it. And you mentioned scale. That's a big deal. So if we think of a typical cylinder bore, roundness is maybe 5 microns, so 200 millionths might be our roundness. That's the size of a smoke particle. A home smoke detector, literally a home smoke detector detects 5 micron smoke particles if it's an optical detector. So, one smoke particle lands inside your cylinder bore, it's out of tolerance for roundness.
Wow. That's some scale. And back to the honing part, scale is one of those things that is one of the light bulb moments when we've given the Trackside Tech Talks. Remember, Joe, that when we say that 100 microinches is equivalent to 1/10 of a thousandth, that people, you can kind of see their heads, kind of pop back. That wakes them up. What did you just say? We're talking about these valleys, and on we'll call it a good high performance cylinder finish, we're talking about that mean line to that deepest valley is usually about 100 microinches, plus or minus, right, a little bit. For them to understand that entire surface finish is a 1/10 of a thousandth per side, which means on a dial bore gauge, that's only 2/10 of a thousandth. And the old way of honing, a lot of guys were taking out, a thousandth or two with their final abrasive. So talk to that, Mark, a little bit about that scale and why it's so important to understand that scale when determining what abrasive you're going to finish with, and then more importantly, how much stock removal you're going to do.
Yeah, and I think that's something that we've learned over the years, and I love the fact that you were experiencing it also when we were talking last week. What we're trying to do is, in any efficient, cost-effective way, we don't want to remove a lot of material. That's wasted time, and you're just throwing the material away. So let me speak to high volume. In a high volume world, we would bore the bore. How's that? Boring a bore. And then use a honing process to clean it up. The honing process is going to clean up the boring marks and get us our initial cylindricity. We're going to make that thing straight and round. Now, lots of high volume OEM manufacturing kind of processes don't just treat that as the surface texture. They're going to use that first hone to get geometry and straightness, roundness, and then come in with a more controlled honing process to lay down the valleys. So we've straightened it out. Now we come in with our really good stuff and lay down a rough surface that's going to give us the valleys. And at that point, we control the size. So laying down the valleys with this rough surface is where size happens. And then we'll come in with a super fine stone and just kiss it for a little while. And I use those words strategically. We're just going to kiss it for a little while, not to size, but for a little while, for time or strokes. So we get a boring operation to clean up the casting, a honing operation to clean up the boring and make it straight, and then valleys and then peaks is traditionally how we handle this in high-volume engines.
Got it. So the valley operation, that is what you're actually using to go to size.
Exactly.
When you finish that, that's your finish size. If your finish size target is 4035, well then your valley operation, your rougher grit, that's to 4035.
And it depends on how rough you're making. Yeah.
Okay.
Yeah, I was going to say it depends on the process, because in some of these extreme cases, let's say your target is 405. We're laying down such a rough texture, we may be targeting 404 because we know the finisher is going to have to do some eating of peaks. And our size measurement was based on those peaks that are going away. So we do have to do a little tuning depending on texture and the size target. And this is the realm we're in, man. This is crazy. We are dealing with textures and sizes at almost the same level of control now. Yeah, we've got super tight size controls, and we're going to make it rough, get our size on rough, and know that we're going to do 11 strokes with a plateau stone that's going to move that a little bit too.
So you could almost begin to kind of compensate that. We know what we're going to need. We're going to take a thousandths out because of how rough the abrasive we're using to go to size is. So we're going to have to go a little bit short of size in order to be able to take out that half a thousandth with our smooth finishing abrasive. That way we have the correct size as well as the correct amount of valley. That way you're not killing the valley to get to size, but you're also not leaving it so rough that you have the right size but the wrong roughness.
Exactly. Yeah, it's a balancing act. We want a rough surface that we can plateau into size. And when we plateau it into size, we magically land in the right place of valleys.
Right. And I think what we've seen, Joe, and from the Trackside Tech Talks and some of the shops we've visited, that for the traditional racing application, that balancing act, we're talking about tenths of thousandths of stock removal to make that happen, not thousandths of inches of stock removal. Some of the old processes guys were using in their head is they would finish to size with, say, a 400 grit, and that may have been taking out a tenth or 2/10, or say a thousandths or 2,000ths of stock removal to do that. So, like I say, you're saying it's not about stock removal necessarily; it's about the time that you're taking in a number of strokes or cycle time to plateau. And I think that's the key thing we're trying to get across, is that it's kind of a change in mentality, because the old way was everything was based on stock removal. Now it's a combination of the two.
Yeah, so an easy way to visualize it is you've got this random surface. It's got peaks, it's got valleys, and my last manufacturing process, the last thing I do to touch it, whether it's a super fine hone or heaven forbid something like a ballizer kind of process, whatever it is, we're going to remove peaks until there's enough material exposed at the top to carry the load. So we're not worried about size with that last fine honing process. What we're worried about is plateauing until there's enough material flat on top to carry the load. The last
Yeah,
process
exactly.
we touch in a plateau honing process is not anything about size. It's about texture.
Perfect. There you go. Yeah, you're honing to size, and then you're plateauing for texture. I like that.
Yeah, that's a great. I like that. We should put that on a T-shirt.
I think we will. Yes. And the next Engine Performance Expo T-shirt. That's going to be what it says. Hone to size, plateau to texture. That's it.
That's it, man.
Nick Ferry is definitely
man.
loving this. I got to tell you, Nick is out there right now, and he's about to click rewind.
We see you, Nick.
Yeah, exactly. Well, it just shows that, for the guys who are into engines, if you have a passion for engines, right? If you listened this far into this episode, this is one of these big levers, that we talked about last week, Mark. This is a big lever you can pull for not only performance, but also longevity, durability, consistency. This is something that you should really have front of mind. And it's not just for cylinder bores. I mean, it's, surface finish for decks, surface finish for camshafts. I mean, it's everything in the engine. That's, how I met Mark was through Billy Godbold when he was looking at these same things. It's not just we have the sizing of these camshafts right, but their problem was the texture, right? That how do we make these camshafts better? How can we support more load so people can be more aggressive in their valve trains? And it was all about not changing the materials. It was about changing the surface texture to create that load-bearing area that Mark was just talking about, that texture that can support a load versus a texture that can't. And you really can't see that with your naked eye.
Well, and you're using the right words, Lake, but I don't know if the listeners know the nuance and the importance of what you said. For example, in the camshaft situation, it wasn't just the surface finish side of texture. See, in the world of surface texture, in the world of surface metrology, we talk about roughness, waviness, and lay. That makes up a texture. Roughness is the fine fuzz, waviness are the lumps, and then lay is kind of the direction that the scratches are going. And the texture in the case of the camshaft is super important because many of those surfaces shouldn't be straight and smooth. In fact, many rolling high-stress surfaces are best if they're slightly crowned. So there's a curvature underneath it. There's a crown shape in roller bearings. So we need to maintain a crown, not just a straight, flat, smooth surface. And then within the crown, the magic is controlling waviness, the lumps on the surface, in addition to the roughness. Here's a way of understanding, do I have a waviness problem? Tear down an engine and see if you see stripes. If you see stripes on a camshaft or stripes on a tappet, that's a waviness problem, not a roughness problem. If it's wide enough for your eye to see stripes, you've got a waviness problem.
That's awesome to think about because, I was there with Billy when they were going through all that learning curve, and to see what they were able to do by addressing the waviness, finding the root cause of the waviness, and then solving it and seeing what they were able to do by eliminating that waviness is big. Because, when we were talking last week, and I've heard you say this before, if you go way back in the day, we talked about the size of things and that the origin of a lot of the sizing equipment all came out of the Revolutionary War. Trying to, I think you said make sure that the musket balls would fit inside the barrel of the gun. Is that right?
Yeah, it's making sure that we had the right size so things could be compatible with each other. Exactly. That was generation one of manufacturing.
All right, so we begin there. So size is important. Then as time goes forward, we start figuring out that contact geometry becomes really important. And that's kind of what we were talking about here is that, okay, if you've got this waviness going on here, well, then your contact geometry really isn't as optimal as it could be. But then there's a next level beyond that, beyond size, beyond geometry, and now it's down to that texture. And what does that texture impart? And that's really where I think this podcast today, this topic of metrology, is so important because that's that next lever to pull in that obtaining that next level of performance. So I'll say here real quick, anyone who's still listening, in the links on the description on the podcast, both here and on YouTube, I'm going to leave Mark's website. Do yourself a favor, go to Mark's website, digitalmetrology.com, and click on the Notepad series. Watch them all in order. It will blow your mind because we're trying to describe all these things with words, and he does a much better job of describing them with pictures. and there's videos. In the waviness video, when you're talking about waviness, I think about that waviness video you made on the Notepad series and how it just you can see it. When you see it, it just resonates. It's the old saying, Joe, right? A picture's worth 1,000 words. I think a good video might be worth like 10,000 or 100,000 words. I'm pretty sure.
Well, it's 30 frames a second, right? So, it's fun, right?
That's
but,
multiple.
to that point, and let me interject real quick. So my job as a surface consultant takes me, every different direction with surfaces. I looked back at about a 2 or 3 window of my consulting gigs where people had parts that worked and parts that didn't, and they didn't know why. And, one supplier makes parts, another supplier makes parts. They're both to spec, but, Fred's parts don't work and Joe's do. I threw that in there for you, Joe.
Thank you.
80% of those problems were solved because they didn't look at waviness. So you can go become a surface metrology consultant and just run around the country and say waviness, 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 and your new career.
Waviness.
Yeah, you win. Write you a check.
Thank you.
Well, both of you guys know this. Everywhere I go, I have my Minitelio SJ210 in my backpack. I am not afraid to check anything, anytime, anywhere, right? It's to me, that was the missing variable. All the years of doing oil formulating, that was the piece that was the variable that I didn't even know was a variable. You just assumed that was being taken care of correctly and it was consistent. And to then finally learn, it's like, no, it isn't always consistent. Back to your Fred's parts and Joe's parts. Well, what's the difference? Well, it's waviness and surface texture, things like that. And if you're not measuring it, you don't have any idea. And you really can't see these things with the naked eye.
I got to tell you guys, my head is spinning, but in a good way, and I think I like it. Now, as we close in on
Put that on a T-shirt also.
That's it. I think I like it. But not everybody that's out there is a high-level pro stock racer or someone working in Formula One. But what I am enjoying and find to be practical is that everything that you guys have just covered applies to everyone all the way down the engine building scale, because it's going to save you time on break-in, right? Like if you can be more consistent with your break-in, if you can be more consistent in your process, if you can make your engines live longer, if you can make them more efficient, that is going to help the engine builder that's listening to Hidden Horsepower grow his business and make money, which ultimately isn't that what it's all about?
Oh, exactly. It just makes their life easier. If you know that this is a variable, and it is, and you know how to grab a hold of that lever now and modify it and move it to your advantage, well, it only helps you. It helps you be more consistent. It helps your brand. It helps your customers feel better about what you're doing, and you can sleep better at night. You don't have to worry because you've essentially conquered or mastered one of these variables that can really play havoc on an engine. And if you can make it run better, then your stuff runs faster, and then everybody's really happy because everybody wants to win races. That's the ultimate goal, right? Let's be real. Right? We all want to go faster. You're competitive. You want to do better, and this is one of those little secrets that's been out there for a long time that you can actually begin to access now and use it to your advantage.
Mark, at the end of each episode of Hidden Horsepower, we ask for advice for the next generation. I'm going to spin that in a different direction because this whole show has been advice for the next generation, frankly. It's been nonstop information. But is there anything that we didn't cover Is there anything that you want to put out there? Is there anything you want to tag this conversation with, in addition to the links that we're going to put up in the description for everyone to go and check out that notepad series, because a picture is worth 1,000 words, but I'm sure everybody's minds are sparking now on this topic. Is there anything you want to say to put an exclamation point on this conversation?
Let me say something super radical, because this has been a very left-brained conversation. We, as technology-minded people, performance-minded people, are always in the analytical side of our brains. A surface is not an analytical thing. It's a shape. It's a piece of art. And if people could go back to the pictures, look at the shape of the surface. At digitalmetrology.com, we just launched a surface library where there are dozens of 3D surfaces. And it's a great way to just, get inspired to say, wait a minute, what are these shapes? And imagine yourself sliding up and down on this surface. Is it a surface you'd want to, use as a slide on a playground and run your kid's butt down it? So I would really say, have that childlike wonder when it comes to a surface.
Excellent. Lake, this one has been tremendous. Did you have a final question for Mark, or?
Oh, I just love that idea of looking at the shapes, like you said, even disregard the scale and just kind of put yourself thinking, what would I want if I'm there? I can look around, if I can feel it, what does this make sense? I love that idea of looking at it more visually and being intrigued by it, as opposed to trying to dissect it and analyze it from a numerical standpoint, but just kind of look at it like you would climb a mountain and look out over the Rockies and see the landscape and just kind of soak it in. I love that idea of the little micron me running around inside an engine, looking at all the landscape, if you will, of all the surface textures. I'm done for the day now. I'm going to be in my own head the rest of the day thinking about that.
Micron me. That's no relation to mini me. Micron me. Mini me's teeny tiny little brother. Well, Mark,
that, Joe. That's awesome.
You've definitely inspired here today. This is what Hidden Horsepower is all about, and I appreciate it. It's funny because you are bringing in a real deep conversation, but you made it easy to think about with your analogies. And sometimes a picture is worth 1,000 words, but it's worth hearing the words to understand what the picture means. And so I think you did a great job. I appreciate you joining us here on Hidden Horsepower. It's been good hanging out with you as well at PRI, and hopefully you will return.
I'd love to. This is so much fun. Thank you so much for the opportunity.
Bye-bye, Mark. We appreciate you taking your time to come today and previously. And, again, we're going to get you back for more in the future. Don't you worry about it.
Awesome. Thank you guys both. Appreciate it.
There he goes. Mark Malburg, Digital Metrology. Wow, Lake, that was intense.
Yeah, I know that when I have my personal kind of scientist friends on the show, we get a little bit intense, like you said, but I think there's value there. Like you said, it's laying out the groundwork. So if you listen to this, now you can go watch the videos and all that, and it will make more sense because now you have the framework to view all that from properly. It'll make a lot more sense, and you'll be able to get a lot further faster. So, again, I can't thank Mark enough for all the help he gives us. I mean, he has been a tremendous asset here at Total Seal, helping us, see the impacts of all these different things we're working on and be able to meet in the middle, if you will, between the engine builders and the honing guys, working with the guys like, Ed Keebler and the guys at Rottler, when we're telling them, okay, here's the numbers we want to see. Well, why do we want to see those? And, maybe we need to modify those numbers and so that the customer gets a better result. That's what's been so great about having Mark, I'm going to call him, on the Total Seal team now, is that we can kind of circle the wagons. We can talk about piston rings. We can talk about honing. We can talk about surface rings. We can talk about oil. We can go full circle to create that ring seal soup now to help our customers get better performance and durability. And that's what the whole goal of the podcast is about, is being able to unlock that hidden horsepower and hidden durability. And I really feel like we got the right team of people now between guys like Mark and Dr. Cantor and Ed and all the guys from Rottler and just Keith and the whole team at Total Seal. We got a pretty all-star group here now, I think.
I definitely agree, and I'm thinking about it in terms of the person who has introduced themselves at PRI to us, right? Hey, I listen to the podcast. I'm trying to run my business, but also make my business better and make things better for my customers. So we listed like 5 things that this is beneficial and touches on all of those touchstones here in this conversation. So, no, great job. Very interesting. Mark's a cool guy, too, as well. Does a lot of media himself, and I appreciate the show. This was great. Now, Lake, for people out there who are listening and they're like, all right, I'm building an engine. I need more information. Tell them how they can get a hold of you or Keith and the folks at Total Seal to evolve their project.
Well, as Mr. Jones always says, make us your first call, not your last call. That way your options aren't limited before you go too far. So 623-587-7400 is the tech line. If you want to just go old school and have a conversation, then call that number. Between myself and Bobby and Kevin and Keith and August, I mean, there's over 100 years of engine building experience under that roof. So that's the easy thing to do, 623-587-7400. But you can also go to TotalSeal.com. Almost all of us have our email addresses on there. You can read up on latest things. We've got the links to our YouTube channel. Our YouTube channel is packed. We have 100 videos now, Joe, on the YouTube channel.
Wow.
From podcast episodes to how-to dyno testing. It's another great resource to be able to learn things from. And, of course, we have regular old email as well. You can send us emails. The request a ring form is a great way. You got a project you want to get an answer on, put it on there, and we'll get back to you.
Excellent. Great job, Lake. This one was tremendous. Thank you so much.
Thank you, sir.
He's Lake Speed Jr. I'm Joe Castello, and this has been Hidden Horsepower. Remember, guys, check out all the social media, Facebook, of course, YouTube. Follow Total Seal Piston Rings. More episodes to come. Hidden Horsepower, Apple Podcasts, Spotify, SoundCloud, and, of course, you can find it on the website. If you like the show, rate and review. That makes a big deal up there in the podcast listings. We appreciate you. You can also follow me, WFO Joe, and I do my own podcast called WFO Radio. You can check that out. If you like drag racing and motorsports, it's up there right next to Hidden Horsepower presented by Total Seal. All right, guys, that's going to do it. We'll see you next time right here on Hidden Horsepower.